Hi, my name is Jonathan Coyne. I am a current physical oceanography master's student supervised by Eric Oliver, and today I will be giving a talk about my research on sea surface temperature trends and variability in the Northwest Atlantic. Briefly, I want to go over just some general circulation in the Northwest Atlantic, although I'm pretty sure most of us are familiar with it. The general circulation of the area is dominated by the Gulf Stream, which brings warm and salty water from the south along the eastern coast of North America before heading off across the Atlantic towards Europe, and the Labrador Current, which brings cool, fresh water from the Arctic towards the Grand Banks area and even goes around Nova Scotia. It is important to note that the path and magnitude of these currents that I just mentioned is not constant, and large spatial scale multi-decadal oscillation in sea surface temperature is an important feature of the Northwest Atlantic. When trying to determine long-term trends and variability in sea surface temperature, with measurements going back 100 plus years, uncertainty in your data is inevitable. This can be seen in the subplots shown here. So I've gathered sea surface temperature data from 5 different historical monthly SST datasets and calculated the sea surface temperature anomaly. Each of these datasets was then spatially interpolated to a common resolution for easy comparisons. From it, I calculated the variance over time of the dataset mean sea surface temperature anomaly. I also calculated the variance across the datasets averaged over time. And then I calculated the normalized interdataset variability by dividing B by A. The normalized interdataset variability shows the disagreement between datasets in many areas of the Northwest Atlantic, including the Gulf of St. Lawrence, Labrador Sea, Denmark Strait, and Norwegian Sea. Differences between sea surface temperature datasets have been noted in the past due to things like data scarcity, differences in interpolation method, and corrections to the source data. This gives rise to the question, which dataset represents true sea surface temperature at a specific location and time? Here, we decide to take a more blind statistical approach, thinking of each sea surface temperature dataset as one realization of true sea surface temperature. From here, we continue with our statistical decomposition of these datasets. So a common way to determine modes of variability in sea surface temperature is to use something called an empirical orthogonal function, or also known as a principal component analysis. For our purposes, an empirical orthogonal function is a way to decompose a spatiotemporal 3D SSTA dataset, or sea surface temperature anomaly, which is shown here on the left, into a sum of orthogonal modes, which contain a PC time series on the top right, and an accompanying EOF spatial pattern, which you can see on the bottom right. The percentage of variability that a certain mode explains can be found by taking its associated eigenvalue and dividing it by the sum of all eigenvalues. In the Northwest Atlantic, the EOF modes 1 and 2, so the leading 2 EOF modes that explain the most variability, have been historically correlated to the Atlantic Multicatal Oscillation and North Atlantic Oscillation climate modes, respectively. A normal EOF analysis doesn't help us with the problem we mentioned before, though, about cross-dataset variability, because it only works for one dataset at a time. Instead, we use a variation of the empirical orthogonal function called an extended empirical orthogonal function. The difference between this is that an extended EOF mode has multiple spatial patterns, for our purposes, each corresponding to one of the 5 datasets. In this way, we can determine variability in a mode's spatial patterns as a result of cross-dataset variability. From this, the mean and standard deviation of those spatial patterns, and also, by extension, the PC time series, can be determined. So instead of comparing separate EOF results from each of the 5 datasets, we can actually determine modes of variability which take into account the before-mentioned differences between sea surface temperature datasets and have one universal set of modes. So it's also worth noting, for the purposes of my research, we are specifically interested in the slope and shelf regions of the Northwest Atlantic, from North Carolina to Labrador. The area is culturally and economically important to a large number of people, and we have seen what type of damage can be caused by extreme temperature events in the region in terms of ocean temperature. It has been suggested that with anthropogenic climate change in combination with multi-decadal oscillation, there will be an increase in the severity and frequency of extreme sea surface temperature events in the Northwest Atlantic. In order to get a better understanding of the shelf and slope regions in the Northwest Atlantic, We followed Chen et al. 2020 and spatially averaged our sea surface temperature data into 21 regions. An extended empirical orthogonal function was then performed on our combined sea surface temperature data set, which has now been spatially averaged into the defined regions of interest. The first three modes were found to be significant under the method brought forward by Overland and Preissendorfer in 1982, and these are shown here in each of the rows, with the first row corresponding to the first mode and the third row corresponding to the third mode. Generally, the modes and spatial patterns were found to be in good agreement with one another and gave us the confidence to combine them to find a mean and standard deviation of each of the spatial patterns, with the mean being shown in the far left column and the standard deviation being shown in the middle. From this, the standard deviation in the time series was also determined, and the time series are shown on the right. The standard deviation is shown by the gray bounds on each of those time series. Although the third mode was determined to be significant, the calculated PC time series uncertainty is consistently close to zero, so the third mode will be neglected for the remainder of this presentation. The first mode shows good agreement with previous studies correlating the Atlantic multicatal oscillation. It is a positive polar structure centered around the Grand Banks and strong multi-decadal signal in the time series. The standard deviation of the spatial pattern is highest at the pole, and its height is highest at the peaks and troughs of the time series. It also explains 58% of the total sea surface temperature anomaly variability. The second mode has a dipolar structure with a positive pole at the mid-Atlantic bight and a negative pole along the Labrador coast. And we can see that in the subplot in the middle on the left there. This is also similar to results from other papers, and it has a strong correlation to the North Atlantic oscillation. It also has a strong multi-decadal variability in its time series, which we can see, with uncertainty highest, again, at the peaks and troughs. It explains 18% of the total sea surface temperature anomaly variability. Correlations between the PC time series and Atlantic multicatal oscillation and North Atlantic oscillation indices were done, and again, good correlation exists between the first mode and the AMO and the second mode with the NAO. But this doesn't really help determine what's the physical forcing behind these modes of variability. Instead of only correlating our PC time series with known climate modes, we took variables from a standard heat budget equation and found time series of their anomalies and determined their correlation with the PC time series 1 and 2 that we were looking at before. The variables time series were also spatially averaged for the regions of interest so that they matched the data, the sea surface temperature data that we were looking at before as well. Atmospheric and oceanic variables include ocean and wind velocity and air-sea heat flux. From these correlations, we could start to infer what was the oceanic response to changes in a specific mode of variability. For this specific plot, we see the correlation of the first two principal component time series we saw before with surface ocean velocity anomaly on the top, depth averaged velocity anomaly in the middle, and surface wind velocity anomaly on the bottom. The areas of each of the subplots were determined by finding the correlation in both the x and y direction separately, corresponding to the u and v velocities of either the surface winds or the ocean velocity, and then making a resulting quiver plot with their values. The colors underneath them show the actual magnitude of the correlation coefficient instead of its direction. Using plots like this, we can say the following sort of things. The first PC time series, which we noted from before, was well correlated with the AMO index, is also well correlated with an enhanced Gulf Stream and weakened Labrador current. And this is true if we look at both the surface ocean velocity anomaly and the depth averaged ocean velocity anomaly. The second PC time series on the right, which again we noted was well correlated with the North Atlantic Oscillation Index, is also well correlated with an enhanced Gulf Stream and Labrador current. This is again true for both depth averaged and surface ocean velocity anomalies. The second PC time series is also well correlated, which is again well correlated with the NO index, is also well correlated with an enhanced surfaced wind westerly. Further correlations were done between the PC time series and air-sea heat flux anomalies. Here we see that the positive correlation exists between the first mode and air-sea heat flux throughout most of the regions of interest, and the opposite occurs in the second mode with negative correlation existing in most regions of interest in air sea heat flux anomaly. We then started to use these comparisons to determine the possible physical forcings behind switches between positive and negative Atlantic multi-decadal oscillation years, following the hypothesis brought forward by Wills et al. 2019. The formation of a positive AMO year occurs when negative air sea heat flux in the Labrador Sea drives Atlantic meridional overturning circulation to affect more warm water northwards. So we see these negative air sea heat flux anomaly terms occurring in a positive NAL year, which you can see in the top left panel. These negative air sea heat flux terms in the Labrador Sea are caused by anomalous westerlies, which we can see in the panel, which in turn enhance deep water formation. So this resulting enhanced Atlantic meridional overturning circulation, you can see in the bottom left panel, brings more warm water northwards to basically counteract this cold water anomaly, which is being caused by this negative air sea heat flux anomaly in the Labrador Sea. And these are starting to be supported by the correlations that I mentioned earlier. The surface and depth average correlations with the first principal component time series also support this, showing an enhanced Gulf Stream during positive years, which follows the same path as the Atlantic meridional returning circulation. And after a sufficient amount of time, increased flow of warm water from the AMOC to the Labrador Current causes the formation of a low pressure cell, which we see at the top right panel. This drives warm air northwards and leads to a positive air sea heat flux throughout the region, which we saw was supported by the correlations with the first principal component and the air sea heat flux term. But eventually, this increase in air sea heat flux into the region, it also increases stratification, slowing down the Atlantic meridional overturning circulation, and causes eventual dissipation of that positive Atlantic meridional overturning or Atlantic multi-decadal oscillation event. Our correlation method with results from the extended empirical orthogonal function support the hypothesis brought forward by Wills et al. 2019. It appears that restricting for the slope and shelf of the Northwest Atlantic does not noticeably change the underlying proposed mechanism. It is important to note that limitations of only using correlations, though, to determine underlying forcings behind climate low regime shifts. Instead, it is important to back up these initial findings using a method that explicitly considers the physics of each region of interest. Currently, I'm working to make a long-term mixed layer depth heat budget for each of the regions of interest as defined here. From this, we hope to get a clearer picture of what causes the variability in SST on long timescales in the Northwest Atlantic slope and shelf. This is the end of my talk. I'd like to thank NSERC, OFI, and Dalhousie. I'd also like to thank Eric Oliver for his constant support with my research.